A second order differential equation is a differential equation that contains second order differential coefficients. What we call a second order differential coefficient is simply a second derivative. For instance, if we have 6 d squared y dx squared minus dy dx minus y equals to x squared, this is a second order differential equation because what we have here is a second order differential coefficient. Solving this is quite different from solving a first order differential equation. So it is a different method that I'm going to explain here. I want to highlight a few things before I start solving this equation. What we call the general solution of a second order differential equation of this format, where to the left hand side we have this, and to the right hand side we don't have a 0, but we have a function of x. When we are solving this equation, the general solution, what I'm going to refer to as y general, is a combination of two functions. One of the functions, we are going to call it a complementary function. So it is y CF. We call that a complementary function. And the other function is called a particular integral. I'm going to call that P. I'm going to call that y pi. So finding the general solution of a second order differential equation essentially means finding the complementary function and the particular integral, and you add them together. That is the general solution, y general. So I am going to explain how you find the complementary function and also how you find the particular integral. I want to highlight that we use what we have on the left hand side to get our complementary function, and what we have on the right hand side to get our particular integral. You should understand this, or you should know this. All right, so the first thing, or the first step when you're solving an equation of this nature is to create what we call an auxiliary equation. We create an auxiliary equation and we solve the auxiliary equation, and the solutions of that auxiliary equation are going to determine the nature of our complementary function. Let me highlight this using this example. I'm going to rewrite this example and then we work it step by step. We have 6 d squared y over dx squared minus dy dx minus y equals to x squared. I'm going to write what is called an auxiliary function or an auxiliary equation. The auxiliary is, in this case, it is 6m. I want to use r. 6r squared minus r minus 1 equals to 0. So our r is like dy dx. That is our r. Some books or some textbooks use m. So you may find it written as 6m squared minus m minus 1. So this minus 1 here is the coefficient of y, and our r is dy dx. That's why here we're using r squared, because this is a second order differential coefficient, and the minus here is there. So please, you need to be able to write the auxiliary. If let's say I had I just want to indicate to you how we write the auxiliary. If I had something like 2d squared y over dx squared plus, let's say, 5 dy dx minus 7y equals to, let's say, x cubed. My auxiliary in this case, the auxiliary, it would be 2r squared plus 5r minus 7 equals to 0. We always equate our auxiliary to 0. I think you can see the pattern of how you can write your auxiliary. It is quite straightforward. Now, we have to solve the auxiliary, and which is essentially solving a quadratic equation. If you know how to solve a quadratic equation, it means you can do this step very easily. And after that, the solutions of that auxiliary are going to tell you the nature of your complementary function. I'm going to explain that. So let's now start by just solving this. Let me take all this out. Okay. So we're going to solve our auxiliary, which is a quadratic equation, as I said. Can we factorize here? If you can factorize, then you factorize it. If you can't factorize, you can't factorize. You use the quadratic formula. So you use whatever you know, all the methods that you know for solving a quadratic equation, you use them here. I think I can factorize this. Let's see if I can factorize this. So there will be a 1 here and a 1 there, and let me use 2 and 3. Do they give me the middle term? So I have a 3r and a 2r here. Okay, if I say 3r times minus r plus, yes, I think this is correct. 3r times 2r, we get 6r squared. Plus 1 times minus 1, we get minus 1. Minus 3r plus 2r, we get minus r. So I have factorized this. From here, it means 3r plus 1 is equals to 0, or 2r minus 1 is equals to 0. It means r is minus 1 over 3, or r is 1 over 2. So I have my r is minus 1 over 3, and my r is, the other r is 1 over 2. These are the solutions of my auxiliary equation. So sometimes, or in fact, since it is the quadratic equation, you can have the solutions being equal. You can also have the solutions being distinct or different, like in our case, or you can have the solutions as imaginary numbers or non-real numbers, or rather what we call complex numbers. So we can have 3 situations, and those 3 situations are going to determine the nature of our complementary functions. It depends on your syllabus. Sometimes you're actually given these situations on your formula sheet and how you write your complementary function. So I'm going to write the 3 situations and how you deal with them. Situation 1, we have r, which is not equals r1, which is not equals to r2, which is our case. If you have that, our complementary function ycf, it will be y is equals to a e to the power r1 x plus b e to the power r2 x. This is the complementary function if your R1 and R2 are real numbers that are not equal, like in our case. Then we have situation 2, I'm going to just call it situation 2, where you have R1 being equals to R2. Your YCF, which is a complementary function, will be equals to y equals to a e to the power R1 x plus b x. So the difference here is that you are adding this x here. E to the power R2x. But in instance, we know that R1 and R2 are the same. So there is no need to put this R1, R2. It's just Rx, because the R1 and R2 are the same thing. If it is 2, both of them are 2. If it is 4, both of them are 4. If it's -1, both of them are -1. That is the situation 2. The third situation is when we have situation number 3. We have R being equals to A plus or minus BI. In essence, these are non-real. This is non-real, or what we call imaginary number. So if we solve our equation, our auxiliary, and the solutions of that quadratic equation are non-real, if we have that, in this case, this a, this small letter a, is a constant, and the b is also a constant. If we have that situation, our complementary function YCF is written as y equals to e to the power of ax. Then you multiply that by a cos bx plus a b sine bx. You close the bracket. This is our complementary function. If this is our complementary function, if the solutions of the auxiliary are non-real, or they're imaginary, as we call them. So now that we know how to get our complementary function in all these 3 situations, let us now go to our equation and then get our complementary function. So we found that our R1 is -1/3 and our R2 is 1/2. We have a situation of R1 not being equals to R2. R1 is not equals to R2, but these are real. They're actually real solutions. The solutions are real. This means our YCF, our complementary function, should be in the form a e to the power R1x plus b e to the power R2x. So in this case, it means our complementary function, let me just call it CF, it is actually y a e to the power, our R1 is -1/3 x plus b e to the power 1/2 x. You are almost halfway. You have solved one part of the general solution. Remember, we said our general solution consists of 2 parts, the complementary function and the particular integral. I said you use the left-hand side of the equation to write your auxiliary function, your auxiliary equation that you're going to solve. And once you solve the auxiliary equation, the nature of your R1 and R2, the nature of your solutions to that auxiliary equation is going to determine also the nature of your complementary function. We did that. We got R1 not being equals to R2. So this is our complementary function. You write that down as a complementary function. Then we move on to now determine our, we now have to determine our particular integral, which is the second part of this question. So half of the question is solved. We go to the second part. The nature of your particular integral depends on the nature of what is on the right hand side of your equation. In our case, we had x squared. To the right hand side of our equation, we had x squared. This means our particular integral will also be in the form of a quadratic function. Our particular integral is actually a quadratic function, but we don't know that. We don't know the particular integral itself. Let me rewrite the question, and then I'll show you how you deal with this situation. We had 6 d squared y over dx squared minus dy dx minus y equals to x squared. I said we use the left hand side, this to get our auxiliary equation, which we solve, and after solving that, we can now deduce our complementary function. But now we use the left hand side to get our particular integral. The nature of what we have here on the right hand side determines the nature of the particular integral too. So what we have here is x squared. It tells us that the particular integral is also a quadratic function. So we have to deduce this quadratic function. We don't know it. So because we know it's a quadratic function, we can write it in general form. So I can say, oh, our particular integral is in the form y equals to a x squared plus bx plus c. This is the general form of a quadratic equation. Ax squared plus bx plus c. Now, I have to find dy dx. From here, dy dx is 2ax plus b. This is my dy dx, 2ax plus b. Then from there, I can also find d squared y dx, the second derivative of this. So the second derivative here, d squared y over dx squared, is simply the derivative of 2ax plus b, which is 2a. Once I have this, I substitute back into this. So I put this one here and there. Where there is dy dx, I put 2ax plus b. Where there is d squared y dx squared, I put 2a. Then I solve for a and b and c. Where there is y, I am obviously, where there is y, I put this. Where there is 2ax, where there is dy dx, I put 2ax plus b. Where there is d squared y dx squared, I put 2a. I'm doing this so that I can solve for my a and b and c. I hope it is clear. You write the general form of your particular integral, and in our case, it is going to be a quadratic function, y equals ax squared plus bx plus c, but we don't know the a and the b and the c. To find the a and the b and the c, we use this general form to get dy dx and to get also the d squared y dx squared, which is the second derivative. Then we substitute back into our original equation. Please note that the form of our particular integral depends on what you have here on the left hand side of your differential equation. On the right hand side of your differential equation, I mean, that's what determines. if we have sine x plus, which is a trigonometric function, it means our complementary function is also likely to be a trigonometric function. There are general forms, guys, given in your textbooks, or you can find them on the internet if you want to. The general form of the particular integral, depending on this function that we have here. So in our case, it is a quadratic function because we have x squared. If we had something like 5x, our particular integral was going to be, let's say, 5x plus 3. It was just going to tell us that our particular integral is also going to be a linear function, which is ax plus b. If we had e to the power, let's say e to the power 2x, here, it was going to mean that even our particular integral was also going to be an exponential function of this nature, e to the power something. That's what it means. So you need to find a list of this format, a list like sort of like a table that will be explaining the nature of the particular integral depending on what you have here. But in our case, as I said, we have x squared, and we assume that our particular integral is also going to be a quadratic function. That's what we mean. Now let's do the substitution of what we have here into our original equation. So this means 6, where there was d squared y, where there was the d squared y dx squared, I'm going to put 2a minus, where there was dy dx, I am substituting 2ax plus b, minus, where there was y, I am substituting ax squared plus bx plus c, and then this is equals to x squared. Let me simplify the left hand side. If we simplify here, we get 12a minus 2ax minus b minus ax squared minus a bx minus a c. This is equals to x squared. I want to group the like terms together. I'll group the like terms together. If you look here, we only have 1 with x squared. So this is minus a x squared. Now I want to put together the coefficients of x. So we have minus 2a and minus b. I'm going to add them. I'm going to group them. So this is like plus minus 2a minus b x. This here is the coefficient of x. Then I put the constants together. So this is plus 12a minus b minus c, all is equal to x squared. This is what I have. Now from here we can compare coefficients. So compare coefficients. What we are saying is the coefficient of x squared to the left hand side should be the same as the coefficient of x squared to the right hand side. So if we look in this case, the coefficient of x squared here is minus a, and this right hand side, it is 1. We can therefore conclude that so coefficients of x squared, it means minus a is equals to 1, which tells us that a is equals to minus 1. So we know our a now. It is minus 1. Okay, now let's move on. We compare coefficients of x. To the left hand side, the coefficient of x is minus 2a minus b And this is equals to 0 because to the right hand side, we don't see any x there. It means the coefficient is 0. But we know our a is -1. It means we can find our b. This means b is equals to -2 times -1. B is equals to 2. Now we have our b is 2. So a is -1, b is 2. We can find our c. On the c, we are not comparing anything. We are comparing constants. So we are comparing constants. To the right, to the left-hand side, the constant is 12a minus b minus c, which is equals to 0 because we don't have a constant on the right-hand side, so it is equals to 0. From here, we can solve for c. If you do your algebra well, you see that c is equal to 12a minus b, which is essentially 12 times -1 minus 2. So 12 minus 1 minus 12 minus 2, that's -14. We now have our a, our b, and our c. A -1, b is 2, our c is equal to -14. Once we have a, b, and c, it means we have our particular integral. So from here, I can write my particular integral, my pi, particular integral, which is y pi, is, remember we said it is in the form ax squared plus bx plus a c, and we know our a is -1, so this is minus x squared plus a 2x, since our b is 2, minus 14 because our c is 14. So this is our particular integral. Now y pi. We have our particular integral. We also found our y cf, which is the complementary function. We have that. So let me write the complementary function also. So y cf, we say this is equals to a e to the power -1 over 3x plus a b e to the power 1 over 2x. This is our complementary function, and we agreed that the general solution is y cf plus y pi. So the general solution is the sum of the complementary function and the particular integral. So all we do here is just substituting into a function. So therefore, our solution to this equation is y equals to, I write my complementary function, which is a e to the power -1 over 3x plus a b e to the power 1 over 2x minus x squared plus 2x minus 14. This is my solution to the second order differential equation. This is the final answer. All right. Even though you may struggle to get the particular integral, at least understand how to get part of the question, which is getting the complementary function. So you can get the complementary function first. It's a fairly easy process. Most people usually get problems when it's getting the particular integral, but it is quite a fairly easy process. Get it right. The other part is about knowing the general forms of the particular integral and also the general forms of the complementary function. I said the general form of the complementary function, this function here, depends on the nature of the solutions of your auxiliary equation, which is essentially a quadratic equation. If you solve the quadratic equation, you get the roots of that equation, which can be real and different, they can be real and equal, or they can be imaginary roots. Because of that, you have three general forms of the complementary function, depending on the nature of the roots of your auxiliary equation. Once you have found the complementary function, you go to find the particular integral, and I said and I repeat, the particular integral, the form of the particular integral depends on the nature of the function that is on the right hand side of your differential equation. If that function is a quadratic function, it means your particular integral is also going to be a quadratic function. If it is a linear function, the particular integral itself is going to be a linear function. So you put the general form of it and then you solve, just like what I did in this example. If you have any other questions that you encounter, or some different forms of these that you may encounter in different textbooks or past question papers, please just comment in the comment section below. I'll look into it and do another video to explain that. But this is simply how you do, or how you solve, a second order differential equation. Thank you for watching the video. Just subscribe to the channel